In this video, I'm going to discuss with you the equation of a plane in dot product form. This is the second form of the equation of the plane. In class, I have already covered the equation of a plane in the parametric form. So this is the second one. As I've discussed also in class, that if you have 3 points, 3 points will be enough to define a plane. If you have 3 points on the plane, you can always find a vector that is perpendicular to the plane by taking the cross product of AB cross AC. Of course, you can have other ways of doing so, but for convenience, I'm just going to take, say, AB, in this case AB cross AC, to give me a vector that is perpendicular to the plane. I'm going to denote this vector perpendicular to the plane as the vector n. I'm going to mark the vector n on this diagram. I'm going to mark the vector n as like this. I can draw it anywhere as long as it is perpendicular to the plane. Right. So given 3 points that define a plane, like I just discussed, I can always find a vector n using cross product that is perpendicular to the plane. Next, if you have a plane, this is a plane. If you see a plane from far, it looks like a line, just like this. So if you see the plane from far and imagine the plane like a line from far, for a plane, you must have at least 1 point on the plane. I've denoted that 1 point as point A here. So bear in mind, if I say a point on the plane, I really mean that starting from origin O, it terminates at the point A on the plane. So this is the position vector of the point A, OA here. And in class, I mentioned before that to talk about the equation of a plane, it is simply an expression that says something about a general point on the plane. How do you mark a general point on the plane here? You can arbitrarily mark a general point as, say, here, the point R. And this is OR. And our intention here is to find an expression that says something about R. And to do this, I'm going to capitalize on what you have learned in the earlier video, the projection. And I'm going to use the concept of projection you learned in the earlier video to tell you how we can find the equation of a plane in dot product form. Now, earlier on, I told you that I can always find a vector perpendicular to a plane. I can draw this vector n, say maybe here, as long as perpendicular to the plane. And because this vector n is like a free vector, I can even draw the vector n here. It doesn't matter whether I draw it as a very long vector n or a short vector n, it really doesn't matter. So look at this diagram here. This vector A and this vector n is like the vector A and the vector B that we saw earlier on. Remember, we had the vector A and B in an earlier diagram. So if you visualize this vector A and n in this way, it looks like the A and B that we had in the earlier video. So if you have A and B or A and n in this manner, and I ask you to find the projection of A onto n. Where's the projection of A onto n? It is actually here. This is the projection of the vector A onto the vector n. By the earlier video, this projection of A onto n is equals to this. Remember in the earlier video, this A is like the A, this n is like the B, so it's like A dot B cap, B cap. But instead of B, now it's n cap and n cap. Likewise, if I ask you to find the projection of the vector R onto n, the projection of vector R onto n is the same vector here to here. And by the same argument, the projection of vector R onto n can be found by taking r dot n cap, n cap. And so these two must be the same vector. And because these two are the same vector, I can then conclude that the multiple of n cap on the left and the multiple of n cap on the right, they must be the same. And removing the modulus of n on both sides, I just get the vector n instead of n cap. And what we have here is an expression r dot n equals to d, where this is a numeral, this number is found by taking a point on the plane to dot product with the normal vector of the plane n. And this concludes our discussion on vector over plane in dot product form.